Let's look at a few calculations for a titration. So here we have an example where we have 25 milliliters of formic acid reacting with 0.1 molar sodium hydroxide. We want to find the pH at a specific point when we've added 12.5 milliliters of sodium hydroxide. So we have a couple of calculations to do. Let's figure out initially how many moles of the acid that we have, so that we can start our calculation by doing moles before moles added and moles after. Now the reason I know that we have to do this particular calculation is because I am looking at the molarities of the acid and the base, and they are the same, which means that our equivalence point is going to be at 25 milliliters of sodium hydroxide. Because our concentrations are equal, our volumes are also going to be equal. So because our 12.5 falls before the equivalence point, we are going to be in the case where we have a buffer solution. So our initial moles of acid is going to be 25 milliliters convert that to liters. We use our molarity. To calculate the moles of our formic acid. And we end up with 2.5 times 10 to the negative third moles. So that is what we're starting with before our reaction. So our HA is 2.5 times 10 to the negative third moles. Our sodium hydroxide before we start is 0, and our A minus is 0. Now the moles that we're going to add, we're adding 12.5 milliliters of sodium hydroxide, or OH minus. And we've got our concentration of the sodium hydroxide. So we're adding 1.25 times 10 to the negative third moles of our base. So the moles that we're adding, 1.25 times 10 to the negative third. Now that is going to react with the acid, neutralizing the acid and forming A minus. So what we're left with is the 2.5 times 10 to the minus third minus 1.25 times 10 to the minus third, which gives us 1.25 times 10 to the minus third. It's going to completely use up our base, but in the process, it is going to form our conjugate base. And so the moles after are 1.25 times 10 to the negative third of the acid, 1.25 times 10 to the negative third of the base. We are going to use the Henderson-Hasselbalch equation, pH equals pKa, the base form over the acid form. Now we need the pKa. And for this particular acid, our Ka is 1.8 times 10 to the negative fourth. So if we want to find the pKa, it's the negative log the Ka, which gives us 3.74. So we can plug that into our equation. And we've got the basic form over the acidic form. Oops, let's put the log in here. That might be helpful. All right, because our acidic and basic form are exactly equal to each other, what that means is that we're going to get the log of 1, which is 0, and our pH is going to equal our pKa. And this happens when we're halfway to the equivalence point for an acid or a base. So here's a practice problem for you to try. This is during the titration of nitrous acid with potassium hydroxide. The Ka for nitrous acid is 4.6 times 10 to the negative 4. See if you can figure out the pH at this point in the titration. Let's start with our chemical reaction. So nitrous acid plus potassium hydroxide gives us nitrite plus water. Now there's a couple things that we need to calculate before we get started. We need to figure out how many moles of acid we have. So if we take the volume times our molarity, and we have to do the same thing for our base. So we've got 5 milliliters times its molarity So what this tells us is that we are not to the equivalence point yet because the moles of acid is more than the moles of the base that we're titrating with. So we are going to be at a point where we are going to have to use the Henderson-Hasselbalch equation. So this means we are going to need our pKa. So our pKa is equal to 3.15. So we are going to be looking at how our moles are changing with time. Okay, so before, added, and after. So for our acid, we've already calculated the moles that we're starting with. The amount of base that we've added is 0.001 moles. And after, again, that base is going to react with our acid, decreasing our acid by 0.001 moles. The base is going to be completely used up, but it's going to form our conjugate base. And so now we can use this in our Henderson-Hasselbalch equation. In order to determine our pH. pKa was 3.15 plus the log of the moles of the base over the moles of the acid. Because we have more moles of acid, our pH is going to decrease. So we're going to have a lower pH than our pKa. Here's another point in the same titration for you to try. So please calculate the pH at halfway to the equivalence point of this same solution. Again, remember that our pKa that we just calculated was 3.15. All right, so if we want to do our calculation here, the key is that we're halfway to the equivalence point. This is where the pH is, we're going to be using Henderson-Hasselbalch. But because we're halfway to the equivalence point, the amount of base and the amount of acid are going to be, or the moles are going to be exactly equal to each other. And so at this particular point, our pH equals our pKa, in this case 3.15. So because we're at this very special point, we know exactly what our pH is.